The need for amplification arises because sensors provide signals that are said to be weak in the millivolts or even microvolts range and possessing little energy. Such signals are too small for reliable processing, which is made much easier if the signal magnitude is increased. Hello everyone, welcome to my channel. My name is Rafael. I am an electrical engineer. And in this video, I would like to invite you to observe the solution of 7 exercises pertaining to signal amplification that frequently appear in exams for electrical engineers. Let's go to the first exercise. Question number 1. The half-rectified sine wave of the figure is to be applied at the input terminals of an amplifier with an amplification factor of -2. The question: draw the output waveform. Let's go to the solution. This is the input waveform, and as the exercise said, it is a half-rectified sine wave. Observe that the amplitude of the voltage between 0 milliseconds and 5 milliseconds, between 10 milliseconds and 15 milliseconds, and between 20 milliseconds and 25 milliseconds is the same and equal to 5 volts, okay? This is in volt and this is in milliseconds. After amplification, the output voltage will be the same at these intervals, okay? After amplification, the magnitude of the output waveform will be the same here, here, and here as well. This is our first conclusion. Secondly, we consider the amplification factor. Take a look at it. The amplification factor, or if you prefer the gain, is V out over V in, which is equal to -2. The exercise said this, that the amount of amplification is equal to -2. Okay, this is the gain or the amplification factor. Therefore, V out is equal to -2 times 5. Alright? Which is equal to -10. Consequently, the output waveform is going to be, this is the input, and the output is going to be okay, my friends, this is the output. Let me erase the input so you can see the output a little bit better. Now only the output is represented in the graph. Okay, my friends? This is a very easy exercise just to begin understanding the theme of signal amplification. Let's go now to exercise number 2. Question number 2. For the circuit of the figure, find the voltage gain, the current gain, and the power gain. Okay, my friends, this is the question. Let's go to the solution. Firstly, we're going to calculate the voltage gain. Observe that Vi is equal to Ri times I, where I is equal to the voltage of the power supply divided by the resistances Rs plus Ri. Okay? Combining these two, we find that Vi is equal to Vs Ri over Ri plus Rs. Okay? Observe also that I0 is equal to the voltage here, 150 times Vi divided by the resistances Ro plus RL. And since VO is equal to IO times RL, we can write that VO is equal to 150 Vi times RL over RO plus RL. Alright? Are you guys understanding? Now combining the aforementioned expressions, we get that VO is equal, we are combining this with this. VO is equal to 150 Ri Vs over Rs plus Ri times RL divided by RO plus RL. Okay? How is it possible? Observe that we have a Vi here, alright? We have a Vi here. We simply substitute. We take this and put here. And the expression becomes this. Thus, the global or overall voltage gain is VO over Vs is equal to 150 Ri over Rs plus Ri RL RO plus RL. Okay? We simply pass this dividing and it becomes this, the expression becomes this, and this is the overall or the global voltage gain. We just need now to use the values provided by the exercise, these values here, and then we find that the overall voltage gain is 40 volts per volt. Okay? Right? Now let's calculate the internal voltage gain. The internal voltage gain does not consider the voltage of the source. The internal voltage gain is, we take from here, okay? VO over VI is equal to 150 RL RO plus RL, and if we substitute using the values provided by the exercise, okay, these values here, we find that the internal voltage gain is 66.7 volts per volt. Okay? These are the voltage gains. This is letter A, what the exercise wanted us to calculate first, the voltage gains. Now we are going to proceed similarly to calculate the current gain. The current gain is calculated using similar steps. Secondly, we calculated the current gain. Observe again that VO is equal to 150 VI times RL divided by RO plus RL. Okay? However, since, let's take a look at the currents, II is equal to VI over RI. And IO is equal to VO over RL. Isn't it? After a little manipulation, we find the expression for the current gain in terms of the voltage gain. Let's do something here. Let's multiply this expression by this. Ri over Ri, which is 1. Anything divided by itself is 1. We can do it. And again, with RL. Now I'm going to pass this RL here in the numerator to here. And this RL in the denominator will stay where it is. And this Ri here in the denominator, I'm going to put below Vi, and this Ri here in the numerator will stay where it is. And the expression is going to become VO over RL equal to 150 times RL over RO plus RL. This multiplying VI divided by RI times RI over RL. Okay? This is the gain. The voltage gain that we calculated in letter A. Okay, this is AV. Here, observe that VO over RL is IO. And observe that VI over RI is II. Then, okay, IO, let me pass this step here. IO is equal to AV times II times RI over RL. Okay? Now I'm going to pass this guy here dividing, and the expression is going to therefore be IO over II equal to AV times RI over RL. And this is the current gain. By definition, the division between the output current and the input current is the current gain. And we are expressing the current gain in terms of the voltage gain here. Okay? Using these manipulations. And we've substituted the values, we find that AI now, AI is equal to the voltage gain. We calculated the voltage gain already. 66.7 multiplying RI 150 kilo ohms divided by RL. RL is 8 ohms. And this is a current gain of 1.25 times 10 to the 6th amperes per ampere. Okay, this is the current gain. And to finish, we're going to calculate the power gain. Letter B, letter C now. The power gain is computed by merely multiplying the current gain by the voltage gain. AP, the power gain is AV times AI, which is, I multiply this by this. This is the voltage gain and this is the current gain. Multiply the two and I find 83.3 times 10 to the 6th watts per watt. Okay, my friends? And this is all for exercise 2. Let's go to exercise 3. Exercise number 3. A certain amplifier operating with a 150 ohms load has a voltage gain of 75 and a power gain of 8,000. With data, determine the current gain and the input resistance. Okay, my friends, this is the question. Let's go to the solution. Taking advantage of what we learned in the previous exercise, we can immediately write that AP is equal to AI times AV. Alright? Which leads to AI equal to AP over AV. Okay? Just taking advantage of the linearity of the problem. Okay? This is a linear relationship. We have this. The exercise gave the power gain and the voltage gain. Then we simply use the values 8,000 watts per watt and 75 volts per volt, and we find a current gain of 106.7 amperes per ampere. In the previous exercise, we demonstrated that AI is equal to AV times the ratio between RI and RL. Hence, to calculate RI, we use the expression in this manner, okay? RI is equal to AI over AV times RL, and substituting 106.7 over 75 times 150 ohms, we find an input resistance of 213.34 ohms. Okay, my friends, isn't it? And it is all for exercise 3. Let's go to exercise 4. Exercise number 4. Determine the output voltage as a function of time and the power gain of the circuit. This is the circuit, and we are going to determine the output voltage as a function of time and the power gain. Okay, my friends, this is the exercise. Let's go to the solution. This data here was given by the exercise, and we shall use it. Letter A, the calculation of voltages and currents in the circuit on the left. Let's begin with this. We're going to calculate voltages and currents in the circuit of the left. Okay? Let's label here I, A, and here IB. Alright, applying another rule, we find that IS is equal to IA plus IB. And in accordance with the data provided by the exercise, the current phasor is going to be 2 phase 0 degrees milliamps. We can write these currents in terms of voltage and resistance. Let's do it. IS is equal to VI over RS plus VI over RI. Okay? If we use the values of RS and RI, we find that IS is equal to VI 1 over 4 kilo ohms plus 1 over 12 kilo ohms. Okay? What we want is VI. Then we manipulate this and we find that VI is equal to 6 phase 0 degrees volts, which translates to this voltage here in the time domain. VI of t is equal to 6 times the cosine of 200 pi t volts. Okay, Now let's do the same for this. Okay? Let's calculate the voltage and the currents in the circuit. AVOC times VI is equal to -10. Okay? This is the amplification factor, -10. Times this phasor here, 6 phase 0 degrees, and this gives a voltage of 60 in the phase 180 degrees. If you prefer, okay, if you do not want to consider the phase, you can simply say that it is equal to -60 volts, alright? I prefer to use the phase, it's clearer. Alright, we can now apply the voltage divider rule here, and we find that VO is equal to this voltage here, 60 phase 180 degrees, times RL over RO plus RL. Okay? Both RO and RL are equal to 1 kilo ohms. And we find that VO is equal to 30 in the phase 180 degrees volts. Okay? Observe that here the amplifier is causing a phase shift of 180 degrees to the signal. Alright? VO, now in the time domain, VO of T is equal to 30 times the cosine of 200 pi T plus 180 degrees volts. Okay? The amplitude was 6 here, and now the amplitude is 30. And the phase was 0, and now the phase is 180 degrees. Then the amplifier, we observe a gain of 5 volts per volt. Okay, 5 volts per volt. 6 times 5 is 30. And also, this is in magnitude. Okay, this is in magnitude. And also, we observe a phase shift of 180 degrees. The amplifier is shifting the signal in phase in 180 degrees. Now let's calculate the power gain. The amplifier, the exercise wants us to calculate the power gain. Let's do it. The power gain is the ratio between the output power and the input power. Okay? The power gain, AP, is the ratio between the output power and the input power. Okay? but the input power is equal to the input voltage RMS squared divided by the input resistance. Observe, it is necessary to mention it, observe that whenever calculating power, we don't consider peak values, we consider RMS values, alright? The input voltage we calculated and we found 6. 6 divided by the square root of 2, okay? The RMS value is the peak divided by the square root of 2. This squared times 1 over the input resistance, which is 12 kilo ohms. And we find that the input power is 1.5 milliwatts. We're going to proceed in the same way for the output power. P out is equal to V out RMS squared divided by the load resistance. This is equal to 30. The magnitude or the amplitude of the output voltage is 30. We need to divide it by the square root of 2 because we are considering RMS values. And we square it and we divide by the load resistance. The output power is in this way 450 milliwatts. Okay? We are now in the possession of the values that we needed. We simply use them. Okay? AP is going to be 450 divided by 1.5, and we find that the power gain as 300 watts per watt. Okay, my friends? And this is all for exercise 4. Let's go to exercise 5. Exercise number 5. 2 amplifiers are cascaded. The first has a supply power of 2 watts, an input resistance of 1 mega ohms, and an input voltage of 2 millivolts RMS. The second has a power supply of 22 watts, a load resistance of 8 ohms, and an output voltage of 12 volts RMS. Based on this information, determine the overall power gain, the dissipated power, and the efficiency. Okay, my friends, this is the exercise. Let's go to the solution. Firstly, we're going to calculate, just to see, we are going to just see some of the parameters that the exercise already gave us. For example, the power supplied by the DC power suppliers. Okay, the exercise gave us this. PDC1 is equal to 2 watts. Okay, this is the power of the DC power supply feeding stage 1 or the first amplifier, and PDC2 is equal to 22 watts. which is the DC power being fed to stage 2. Okay? Let's calculate the dissipated power on Ri1. Ri1 is here, and its resistance is 1 mega ohms. Okay? P I1, okay? The input power, which is also the dissipated power on Ri1, okay, is 2 millivolts. We don't have to divide it by the square root of 2 as we did in the previous exercise, because the exercise here, exercise 5, already stated that this value is RMS, okay? It is not peak. So, as it is already RMS, we don't have to divide it by the square root of 2. Squared divided by 1 mega ohm. And this is equal to 4 times 10 to the negative 12 watts, which is equal to 4 pico watts. A very, very extremely weak signal in power. And let's see. Let's do the same for the output power. The output power is the power dissipated in the load resistor PO, which is PO2, okay, following the nomenclature here, which is equal to 12. The voltage that the exercise gave us already in RMS, squared divided by the resistance, which was given as 8 ohms. And this is equal to 18 watts, okay? Oh, what a jump! From 4 picowatts to 18 watts. And how about we calculate now the here? The total power delivered by the DC sources is 24 watts. 2 plus 22 is 24 watts. Okay, and with these two we can calculate the power gain. The power gain is going to be AP is going to be PO2 divided by PI1, or if you prefer, simply PO over PI, which is equal to this divided by this, which is 4.5 times 10 to the 12th power watts per watt. Okay, a very big power gain. Okay, which in decibels is, let's put it in decibels, 10 times the logarithm of 4.5 times 10 to the 12th, which is equal to 126.5 decibels. All right. We calculated already. The power gain. the dissipated power. Let's calculate the dissipated power. This is the other parameter that the exercise wants us to calculate. Let's calculate it. Okay, have you guys fully understood how to compute the power gain? Now let's calculate the dissipated power. The internal dissipated power, internally in the stages will be, take a look at it. As the input signal is extremely weak, okay, we saw it was 4 picowatts, 10 to the negative 12. We don't need to take account of it, okay? The power in plus the powers supplied by the DC sources have to be equal to the dissipated power plus the power delivered to the load element, which is the output power. But since this is extremely small, we are not going to consider it, okay? It's irrelevant. And the dissipated power is going to therefore be merely the PDC minus PO, which is 24 watts minus 18 watts, which is equal to 6 watts. 6 watts is the power that is dissipated in the stages, alright? Stage 1, stage 2. Alright, now to finish we can calculate the efficiency. The efficiency is going to be PO over PDC times 100%. Why we consider PDC instead of Pin? Because we are accustomed to calculate efficiency based on P out divided by Pin. We observed that, once again, I'm going to mention the input power coming from the signal, which may be coming from a transducer or a sensor, is extremely small, 10 to the negative 12 in picowatts. So instead of considering it, we consider the DC sources that provide a whole lot more power to the amplifier, and then it is 18 watts divided by 24 watts times 100%, and this is an efficiency of 75%. Okay, my friends? And this is all for exercise 5. Let's go to exercise 6. Exercise number 6 now. The figure depicts an amplifier composed of a cascade of 3 stages. Compute the overall gain, the current gain, and the power gain. And the exercise also gave us this information here that we shall use. Okay, my friends, this is the question. Let's go to the solution. First of all, we are going to compute the voltage gain from VI1 to Vs, okay? Observe that VI1 is Vs Ri1 over Ri1 plus Rs. Okay, we can simply apply the voltage divider rule here to find Vi1 in terms of Vs. And if we use the values, Ri1 is 1 mega ohms and Rs 100 kilo ohms, we find that the voltage gain from VI1 to Vs is VI1 over Vs equal to 0.909 volts per volt, okay? This is actually an attenuation rather than an amplification. We observe that VI1 is actually smaller than Vs. This is the contrary of what we want. We want amplification rather than attenuation. Let's see the other gains and have conclusions about attenuation and amplification. The voltage gain of the first stage is obtained by considering the input resistance of the second stage, the input resistance of the second stage as the load of the first stage. Okay, this is the input resistance of the second stage. We are going to consider it as the load of the first stage. Okay, and we're gonna see that AV1 is equal to VI2 divided by VI1. And since we can apply the same voltage divider rule here to compute VI2, we know that VI2 is equal to 10 times VI1. Applying the voltage divider rule, we find that RI2 divided by RI2 plus RO1, okay? And using the values RI2, 100 kilo ohms, RO1, 1 kilo ohms, we know then that AV1, the first voltage gain or the voltage gain of the first stage is equal to 9.9 volts per volt. Okay, this is the voltage gain of the first stage. We can see now that VI2 is larger than VI1. Okay, here it was an attenuation, but now we are getting amplification. Let's do the same for the other stages. Similarly, the voltage gain of the second stage is obtained by considering the input resistance of the third stage, as the load of the second stage. Okay, this is the input resistance of the third stage, and we are going to consider it as the load of the second stage. And we apply the voltage divider rule here to calculate VI3 as 100 VI2 times RI3 divided by RI3 plus RO2. We're going to use the values. RI3 is 10 kilo ohms, RO2 1 kilo ohm. Okay, in this way we pass this below here. Okay, VI2 we pass below VI3, and we use the values, and we find that the voltage gain of the second stage is 90.9 volts per volt. Finally, the voltage gain of the output stage, the voltage gain of the third stage, is going to be gotten considering the load as the output of this stage here. Okay, the output stage. And we are going to calculate VL now. Okay, this VL is equal to 1 times VI3 RL over RL plus RO3. Okay, and we pass this below here, and we use the values. RL is 100 ohms and RO3 10 ohms, and in this way we find that the voltage gain of the third stage is equal to, again, attenuation, 0.909 volts per volt. Okay, this is the voltage gain of the third stage. All right, we have calculated the voltage gain of the three stages, and we are going to calculate now the overall, the global voltage gain. And the total gain of the three stages in cascade is obtained by merely multiplying the gains. AV is going to be equal to VL over VI1. Okay, this is the internal voltage gain. The internal voltage gain, not yet the global or overall voltage gain. The internal voltage gain is going to be A V1 times A V2 times A V3, and this is equal to 818 volts per volt. All right, which translates to a gain in decibels of, we can write this in decibels, AV in decibels by multiplying it by 20 times the logarithm and taking the logarithm of this. And we find 58.2 decibels. This is the voltage gain, the internal voltage gain from the stages, written in volts per volt and here written in decibels. Okay, now we are going to calculate the overall voltage gain, or the global voltage gain. The overall global voltage gain, that is from source to load, is also obtained by multiplication of the partial gains. The global gain is VL over VS, which is equal to AV, what we just calculated, times VI1 over VS, and this is equal to 818 times 0.909 volts per volt, and this is equal to 743.6 volts per volt. And we can also convert this into decibels. It is going to be in decibels 20 times the logarithm of 743.6, which is equal to 54.4 decibels. Okay, this is the voltage gain in decibels, the global voltage gain from load to source. All right, now we are going to calculate the current gain. Let's calculate the current gain now. The current gain is going to be the output current divided by the input current. The output current is a division between VL, the voltage on the load, divided by the load resistor, the resistance of the load resistor, and VI1 here, divided by RI1. Remember that we are calculating current. IO is this and II is this. IO is VL over RL and II is VI1 divided by RI1. And we then find that it is equal to VL over VI1 times, we are going to substitute RL 100 ohms, I1, 1 mega ohms. And this is 1 mega ohms divided by 100 ohms, okay? Which translates to a current gain of 8.18 times 10 to the 6th amperes per ampere, or in decibels, you simply do this. AI in decibels is equal to 20 times the logarithm of 8.18 times 10 to the 6th, which is equal to 138.2 decibels. Okay? This is the current gain. Lastly, we calculated the power gain by multiplying the voltage gain and the current gain. AP, the power gain, is equal to AV times AI. And this is equal to, we multiply this. This is in decibel, but this is in amperes per ampere. We use the value in amperes per ampere. We use the value of the voltage gain that we calculated, and we get a power gain equal to 66.9 times 10 to the 8th watts per watt. And to convert this into logarithm, we don't multiply by 20. Remember this, we multiply by 10. So the power gain is in decibels is equal to 10 times the logarithm of 66.9 times 10 to the 8th, which is equal to 98.2 decibels. Okay, my friends, this is all for this exercise. Let's go to the last. Let's go to exercise 7. Exercise number 7. For the secret of the figure, letter A, derive an expression for the amplifier voltage gain as a function of frequency, the DC gain, and the 3 decibels corner frequency. Letter B, calculate the values of the DC gain, the 3 decibels frequency, and the frequency at which the gain becomes 0 decibels. And letter C, find the output voltage in the time domain for the input voltage of Vi of t equal to 0.1 times the sine 100t volts. Okay, my friends, this is the question. Let's go to the solution, and let's begin with letter A. Utilizing the voltage divider rule, we can express Vi in terms of Vs, but pay attention that Vi is not only the voltage across Ri. Vi is also the voltage across the capacitor. Okay, so we're gonna need to combine them in a parallel connection to properly get Vi, alright? So Vi is equal to Vs times Zi divided by Zi plus Zs. Okay? Where Zi is the impedance resulting from the parallel connections between Ri and Ci. So Zi is the impedance resulting from the parallel connection between this resistor and this capacitor. In the frequency domain, Zi of S is equal to the parallel connection between the resistance of the resistor and the impedance of the capacitor. We're going to call it Zc. Okay? Where the impedance of a capacitor is 1 over Sc. Okay? Continuing, we find that Zi of S is equal to Ri over Sci divided by Ri plus 1 over Sci. It is the product divided by the sum, okay? When there are two impedances connected in parallel like this, in the numerator it is the product, in the denominator the sum. And we find that Zi of S is equal to Ri over Srici plus 1. Working a little bit more on this equation, okay, we transfer this to this, okay, this to this, and knowing that Zs here, Zs is Rs, Zs is Rs, okay. This is only resistance, and this is the parallel connection between a resistance and a capacitance. We find that Vi over Vs is equal to 1 over 1 plus Rs over Ri plus Sci. Okay? This expression can be put in the standard form of a low-pass single-time constant network. This is the standard form. I'm going to put it here. K over 1 plus S over WO, in which WO, 1 over tau, is the time constant of the network. For us is RC. Okay? WO is the half power cut off or corner frequency. You choose how you are going to consider it. It is the half power frequency, the cut off frequency, or the corner frequency, and tau is the circuit's time constant. Okay, considering this, which is the standard for low pass single time constant networks, we are going to rewrite this in this fashion here. And we are going to do this. Vi over Vs is equal to 1 over 1 plus Rs over Ri times 1 over 1 plus Sci Rs Ri divided by Rs plus Ri. Okay. And what is this? This is the gain. Okay? This K here, it is the gain of the STC network. 1 over 1 plus Rs over Ri. This is the gain of the network. In this case, it is a low-pass network. And observe here, okay? Observe here. Compare this with this, and we find that WO, which is the corner frequency or the half power frequency, is 1 over Ci Rs Ri over Rs plus Ri. Alright? Which can be also rewritten as this. Rs plus Ri divided by Ci Rs Ri. Alright? At the output side of the amplifier, it is possible to use the volt divider rule to write. Okay, now we are going to consider the output side. It is simpler here because we do not have a capacitor as we had here. We have only resistive elements. Okay, hold this, we are going to use it later, but let's forget this side and pay attention to this side now. VO is equal to mu VI RL over RO plus RL, okay? Which leads to VO over VI equal to mu RL RO plus RL. Now to compute the overall or global voltage gain, we combine the results obtained until here, okay? To compute the global voltage gain from VO to VS, we are going to use everything that we calculated up until here, okay? VO over VI times VI over VS. We calculated first VI over VS, and secondly we calculated VO over VI, and this is VO over VS from load to source. And we simply multiply the results that we calculated, and we find that VO over VS is mu 1 over 1 plus RS over RI 1 over 1 plus RO over RL one plus SCI RS RI RS plus RI. Okay, and this is the expression that combines what we got up until here, okay, and it represents the gain from VO to VS. All right, the exercise wanted us to precisely do this. Let me refresh my mind. The exercise in letter A stated that we should derive an expression for the amplifier voltage gain as a function of frequency. Okay, it is expressed here as a function of frequency. This is the frequency. Okay, when the behavior of resistors do not vary much with frequency, but for capacitors there is a huge difference between how capacitor behave for low frequencies and high frequencies. Then we need to assess how the circuit containing these sort of elements such as capacitors and inductors behave as we increase the frequency. So that's it. This is the expression in terms of frequency. Now the exercise wants us to calculate the DC gain. The DC gain is obtained by setting the frequency to 0. We're going to set this here, set to 0. Okay, when we set this to 0, we get the gain. K prime is the gain from load to source, which is VO over Vs at S equal to 0, which is equal, K prime is equal to nu 1 over 1 plus Rs over Ri, 1 plus Ro over Rl. Okay, this is the DC gain, where K prime is the gain from source to load, while K is the internal gain from output to input. Okay? How about the 3 decibels frequency? The 3 decibels frequency, we have already expressed it. The 3 decibels frequency is WO equal to Rs plus Ri divided by Ci Rs Ri. You simply use the values. The exercise gave Rs, Ri, Ci, Rs, and Ri. And if you use the values, you are going to find the gain and the 3 decibels frequency. Okay, my friends? And this is all for letter A. Let's go to letter B. Alright, what did letter B want? Calculate the values of the DC gain, the 3 decibels frequency, and the frequency at which the gain becomes. Alright, we're going to simply substitute the values for letter B. Simply substitute the values. K prime is equal to 144. Okay, 144 is the amplification factor. Okay, 1 over 1 plus Rs. Rs was given as 20 kilo ohms divided by Ri. Ri 100 kilo ohms. And the same here, 1 over 1 plus Ro. Ro is 200 ohms divided by Rl. Rl was given as 1 kilo ohms, 8,000 ohms. And this gives a value of 100 volts per volt. Okay? This is the gain from load to source, the overall gain. This is the overall gain, which translates to decibels as this here expressed in decibels is equal to 20 times the logarithm of 100. Observe that we have to take the magnitude of the value, okay, and this is 40 decibels. Now for the 3 decibels frequency, let's calculate for the 3 decibels frequency. For the 3 decibels frequency, we use the values of the capacitor and the resistor. We came up with the expression for the 3 decibels frequency. We use the values, okay? The 3 decibels frequency is Rs plus Ri. Rs is 20 kilo ohms, Ri 100 kilo ohms divided by the capacitor 60 picofarad times Rs 20 kilo ohms times the Ri, which is 100 kilo ohms. Okay, and this is 10 to the 6th radians per second. Okay. And S as W is equal to 2 pi times F, we find that the frequency in Hertz is 159.2 kilohertz. Okay? Since the gain of a low-pass SDC network of first order low-pass filter falls off at the rate of negative 20 decibels per decade, starting at W0, the gain will reach 0 decibels in 2 decades. Okay? We are going to chart the magnitude plot of this filter, this amplifier. For more on frequency filter, watch the video I left on my on the description of the video. Okay, I'm going to leave a video related to filters in the description of the video so you can understand more of what I am going to draw here. Okay, this here is the magnitude in terms of frequency. Okay, and this is W over WO, where WO is the corner frequency. We have here 0, 10, 20, 30, and 40, and here 1, 10, and 100. Okay, here and here. Okay, but pay attention that we have a knee here. We have a knee here. There is a deviation. There is a deviation, 3 decibels deviation here from the linear line approximation to the actual curve. Okay, and we know that this falls off at a rate at 20 decibels per decade. 20 decibels per decade. This is 1 decade. This is 1 decade, okay? From 1 to 10 is 1 decade. And it falls 20 decibels per decade. It is 40 at 1 and 0 at 100. Here it is 20. Okay? And this is the magnitude plot in decibels. Okay? In decibels. The unit gain frequency is the frequency for which the gain decibels is 0 decibels. Which in this case is, alright, this is the ratio of the actual frequency by the corner frequency. Alright, W over W0 equal to 100. This is the frequency 100 here, where the magnitude in decibels falls to 0 decibels. Okay, then the frequency where it happens is 100 times WO, 100 times the knee frequency, which is equal to W is equal to 100 times the corner frequency, 10 to the 6 radians per second. We calculated it. And 100 times it is 10 to the 8th radians per second, or if you prefer, a frequency in hertz equal to 15.9 megahertz. All right. Okay, the exercise asked us in letter B the frequency at which the gain becomes 0 decibels. This is the ratio when the ratio W over WO is 100, the magnitude in decibels is 0 decibels. Then the frequency is going to be 100 times this, and we found 10 to the 8th radians per second, or 15.9 megahertz. Okay, now let's finish and work on letter C. Letter C wanted us to find the output voltage for the input voltage equal the input voltage Vi of t equal to 0.1 times the sine of 100t. Okay, we want to compute the output voltage provided that the input voltage is this. The phasor, the corresponding phasor is 0.1 phasor 0 degrees volts. If we use the transfer function, we calculated a transfer function. If we use the transfer function, T of JW, okay, for S equal to JW, T of JW is equal to 100. They found a gain equal to 100. 1 plus J 10W times 10 to the 6th. Okay, as the angular frequency of the input signal is the angular frequency of the input signal is 100 radians per second. Okay, and if we substitute this here for the frequency of 100 J100, it is 100 1 plus J 10 to the negative 4. Okay, now let's work on the magnitude. The magnitude of this. Okay, complex numbers have magnitude and angles. The magnitude of this is going to be the magnitude of T of J100 is equal to 100 squared divided by 1 plus 10 to the negative 4 squared, and the square root of it all, which is a magnitude approximately equal to 100. Okay, because 10 to the negative 4 squared is 10 to the negative 8. 1 plus 10 to the negative 8 is approximately 1. Okay? 10,000 divided by 1 is 1. The square root of 10,000, we return to 100. Now the angle is equal to the negative of the inverse tangent of this over this, because the angle of the numerator is 0. The angle of the denominator is the inverse tangent of 10 to the negative 4, and this is approximately 0 degrees. Consequently, T of JW, where W is 100, can be written as 100 phase 0 degrees. And to calculate the output phasor, we multiply the transfer function by the input phasor, and we find 10 phase 0 degrees. And to finish, we convert this to the time domain, which is equal to 10 times the sine of 100 t volts. Okay, my friends, and this is all for exercise 7, and for this video, comprising signal amplification. I hope you enjoyed the video and learned from it. I am a teacher. If you want to book a lesson with me, use my WhatsApp number, guys. Goodbye.